Okay, this is lecture 11, and we are continuing on to limits. Remember, we got the notation for limits that looks like this, and the way we say it is the limit as x goes to a of the function equals L. And something that you might see, let's just do a quick example. If I had, say, a parabola that looked like this, y equals x squared. And I wanted to know the limit as x goes to -1 of x squared. Well, I know that that point right there is -1, 1. And if I'm looking from the left, I'm going to -1 from the left, that's here. It goes to 1. The y value goes to 1, is getting closer and closer to 1. If I'm going to the right, the y value is also getting closer and closer to 1. So we say the limit as x goes to -1 of x squared equals 1. All right, and we saw some of them off of a graph. We also looked at a table and computed to see what number it was getting close to. But now we want to compute some of them algebraically as well. So let's take a look at this graph, and then we will look at some algebraically, and then we'll also look at what happens at the ends towards -infinity and to infinity. All right, so let's take a look at this graph here. Number 1, it says find the limit as x goes to -3. All right, so -3 is right here. So from the left, it's going to 0. From the right, the y value is also going to 0. It's not defined at 0, but that's okay. All right, so the limit is 0. Let's take a look at x equals, or number 2, the limit as x goes to -2. All right, so that's where I have this asymptote here. If I'm looking as x goes to -2 from the left, it's going off to positive infinity. If I'm looking at -2 from the right, it's also going off to positive infinity. So the limit is infinity. Now, there's a lot of argument among some mathematicians if this limit really exists. A lot of people say that if there's an asymptote, it doesn't exist. But in our textbook, they're saying if they both go to the same infinity, positive infinity, or both to negative infinity, then the limit is infinity. All right. Negative number 3. X goes to -1 from the left. So here's -1. From the left is this side. So from that side, the y value is 1, 2, 3. Now they're asking on number 4, the limit as x goes to -1 from the right. So that's from this side. And that is going toward 0. All right, and since 3 and 0 are not the same, we say the limit on number 5, the limit as x goes to 1, -1, does not exist. All right, number 6, it says the limit as x goes to 2. So here's 1, 2. Now we see that it's defined up here, but we don't really care about where exactly it's defined. We care about what it's getting close to when I come from the left and from the right. So from the left, I'm going to 1, 2, 3, -3. That's towards here. From the right, it's also going towards -3. So the limit is -3. Now the last one is the limit as x goes to 4. So 1, 2, 3, 4. All right, so it's that point right there. So from the left, it's going to 0. From the right, it's going to 0, and it's even defined there. So the limit is 0. Excuse me. All right, so that's from a graph. Now what we want to do is we want to do limits by direct substitution. All right, and we can do direct substitution as long as it is defined where we're taking the limit of. All right, so if I look at the first example, and we looked at a lot of these properties on lecture 10, but we didn't get to do a lot of examples. So let's do some of those. And I can plug in -3, right? If I just plug in -3, I'm not going to get something that's undefined, right? So I'm just going to get e to the -3 squared plus 2 times -3 minus 3. So that gives me e to the 9th minus 6 minus 3. So that gives me e to the 0, which is equal to 1. All right, now let's take a look at some rational functions. And these are going to work the same way as long as it is defined there. All right, so if I'm looking at this example right here, if I plug in 1 into the denominator, I'm going to get 2. I'm not going to get 0 in the denominator, so I can do a direct substitution. It's when I get a 0 in the denominator that there's a problem. All right, so I'm going to directly plug in. So 3 minus 1 over 1 plus 1, and we get 2 over 2, which is equal to 1. All right, now if we look at this next example, if I plug in -3, I do get 0 in the denominator, and that's a problem. But oftentimes we can do some algebra, do some cancellation, do some algebraic manipulations so that we can rewrite it in such a way so that I don't get a 0 in the denominator. So that's what we're going to do here. The limit as x goes to -3. I can factor the denominator as x minus 3, x plus 3. And remember, with these type of functions, what we have found is if I can cancel out the one that's causing a problem, I end up getting a hole there, right? So not an asymptote, but a hole. I will on this one, let's see. I will have an asymptote at x equals 3, but at x equals -3, there will be a hole. So now what happened is I canceled it out, and now I can directly substitute, right? Because now if I plug in -3, I will not get a 0 in the denominator. So I get 1 over -3 minus 3, which equals -1/6. All right. Now, so again, a lot of times what we have is we have something of the form 0 over 0. All right. And we don't learn as much about this in this class. If you take the STEM calculus, you learn about L'Hopital's rule. But again, what we're going to do is if I get something that looks like 0 over 0, that means I definitely have a way that I can do some type of manipulation so that I can cancel out the one that's giving me a problem in the denominator so that the denominator is not equal to 0. So if we take a look about the intermediate forms, and you can use L'Hopital's rule, we're not going to do that in this class, but just thought I would mention it. So what I have here, if I plug in 3 into this example right here, I get a 9 minus 3 minus 6, which is 0. And then in the denominator, if I plug in 3, I get a 9 minus 9, which is also 0. So that tells me I should do whatever algebraic manipulations I know how to do. That includes factoring. In a minute, we'll see one that is multiplying by the conjugate so we can rationalize the numerator or the denominator. But typically, if you see something that looks like a rational expression, a rational equation, then you should start with factoring, right? So I can factor the numerator as x minus 3, x plus 2. And I'm going to factor out just an x in the denominator. So I get a 3 minus x. Now, if you notice, this factor here in the numerator and this factor here in the denominator, they're not the same, but they're just off by a negative sign. So what I'm going to do is I'm just going to factor out a negative sign from the denominator. So let's see. X goes to 3, x minus 3, x plus 2. if I factor out a negative sign, I'm going to get a -3 plus x. All right, and you can check to see that we haven't changed the problem. If you multiply through by -x, notice you're going to get the exact same thing that we had in our original problem. All right, but now since I have a -3 plus x, that's the same thing as x minus 3, and I can cancel. And I'm going to rewrite it without those factors, and I get an x plus 2 over -x. Now, if I plug in 3 to the denominator, I don't get a 0 in the denominator. So now I can do a direct substitution. So I have a 3 plus 2 in the numerator and a -3 in the denominator, or a -3 in the denominator, and I get a -5/3. All right, so always try factoring if you have a rational function. All right, so now here's an example. Again, if I plug in 3, I plug in 3 here, I get a 12 minus 3, which gives me the square root of 9, and I get a 3 minus 3 in the denominator. So I get a 0 in the top, and I get a 0 in the denominator. All right, so that means that I should be able to find the limit, and I should try some algebraic manipulations. All right, and in this class, when we see a square root with a limit, we are always going to do the same thing. We're going to multiply the top and the bottom by the conjugate. Remember, I can't change the function, but if I multiply the top and the bottom by the same thing, that's the same as multiplying by 1. So that does not change the problem. So the conjugate of the numerator is x plus 12 minus x. Remember, the conjugate is just changing the sign in front of the square root. And again, x plus 12 minus x. Now, what we're going to do is we are going to FOIL on the top. And the reason why we use a conjugate is because you get rid of the middle terms. So what's going to happen is we're going to get rid of our square root. In the denominator, do not FOIL, all right? Do not FOIL the one that didn't have a square root to begin with, because if you do, you're going to lose the factor that you should be able to cancel out. All right, so in the numerator, I have an x times an x, which is an x squared. I have an x times a square root of 12 minus x, and then I have a negative square root of 12 minus x times x, and then I have the square root of 12 minus x times the square root of 12 minus x. One has a negative sign, one has a positive sign. So I'm going to put a negative sign, and then when I multiply a square root times a square root and they're the same, I just get what's underneath the square root. So I get a 12 minus x. All right, and again, like I said, do not multiply out the denominator. Just leave them exactly as they are. All right, so let's do some adding like terms in the numerator. So like I said, we want to get rid of the middle terms. That's what happens when you when you multiply by the conjugate. So those two terms cancel. And then I'm going to distribute that negative sign. So I get a plus x minus 12. And I'm going to leave the denominator exactly the same. Now I can factor the numerator. So I have an x plus 4, x minus 3. And there you see that we have that factor of x minus 3 in both the top and the denominator. Had we multiplied out the denominator, we would have not seen that factor possibly. So I'm going to cancel those, out of room. So I have the limit as x goes to 3 of x plus 4 over x plus the square root of 12 minus x. Now, when I plug in my 3, I do not get a 0 in the denominator, and that's what we want. We don't want to have a 0 in the denominator. So I'm going to do my direct substitution now, so that I have a 3 plus 4 in the numerator and a 3 plus the square root of 12 minus 3 in the denominator. This gives me 7. 12 minus 3 is 9. The square root of 9 is 3. So I have a 3 plus 3, which gives me 6. All right. last example, I have a fraction within a fraction, right? So what we want to do is we want to get rid of that. And the easiest way I believe to do, there's a couple different ways. You can find a common denominator in the numerator and then simplify. But I think one of the easier things to do is just multiply by the common denominator that's in the numerator. And again, we don't want to change the function, so we're going to multiply it by the top and the bottom. So in the numerator, the common denominator is a plus h minus 3 times a minus 3. And we're going to do that on the top, and we're going to multiply it on the bottom. All right, if I multiply this term right here by a plus h minus a minus 3, the a plus h minus 3 is going to cancel, and I'm going to be left with a minus 3. Now, if I multiply the second term by a plus h minus 3 times a minus 3, the a minus 3 is going to cancel, and we're going to be left with a plus h minus 3. Notice there's a negative sign in between it, so we need to make sure we don't lose that negative sign. And I'm going to put the a plus h minus 3 in parentheses. Right, in the denominator, I'm just going to leave it just like that. So now I have an h times an a plus h minus 3 times an a minus 3. Right, in the numerator, let's add like terms. I have an a minus a, and I have a negative 3 minus negative 3. So I'm left with a negative h over h times a plus h minus 3 times a minus 3. Now I can cancel my h in the numerator and the denominator. So what I'm left with is a negative 1 in the numerator and the a plus h minus 3 times a minus 3 in the denominator. Now if I plug in 0, I'm not going to get a 0 in the denominator. So that's exactly what I'm going to do. So I have an a plus 0 minus 3 times a minus 3. Well, a plus 0 minus 3 is the same thing as a minus 3, so I'm going to write it as negative 1 over a minus 3 squared. All right, so those are the most types of examples, or the typical type of examples that you're going to see show up in this class. All right, so now what we want to do is we want to think about limits at infinity, meaning out here by positive infinity and down here by negative infinity. So this is as x goes to infinity, and this is as x goes to negative infinity. All right, so if we're looking at this particular example, notice there's an asymptote here at y equals 1. Right, there's that asymptote, that line at y equals 1. The limit as x goes to infinity of this function, x squared over x squared plus 2. When I get towards positive infinity, when I get really, really big, what is the y value that it's approaching? Well, it's approaching that asymptote. All right, so that limit is 1. And it's the same thing if I took the limit as x went to negative infinity of that function, because as it goes to negative infinity, it's going towards that asymptote as well. All right, we could look at it as looking at the table, right? As I get really big, notice, so here's x getting bigger, 1, 10, 100, 1,000, 10,000. What's the y value doing? Well, it's getting really, really, really close to 1. All right. Now, if I take the limit, and this should remind you, remember when we talked about finding asymptotes, we looked at, okay, if the degree of the numerator was the same as the degree of the denominator, then the asymptote is the leading coefficient over the leading coefficient. So in our case, 1 over 1. All right, and that happens to be our limit as I go to infinity. Well, that's the way we do it algebraically, is looking at the degrees. But the way you do it if you were doing it with calculus is you take the limit as it goes to infinity. And if you get a constant out, then that is your horizontal asymptote. All right, so if I take the limit as x goes to infinity of a function, and that function equals some number L, then that is y equals L is your horizontal asymptote. All right, and that's if I go to positive infinity or negative infinity. And they don't necessarily have to be the same. You could definitely have a function that looks like, well, here's a trig function that I'm thinking of, inverse tangent. But it looks like this. And there's an asymptote here, and there's an asymptote here. So it goes off to positive infinity. It goes to one asymptote. As it goes to negative infinity, it also goes to a different asymptote. But if I take the limit as it goes to infinity, that value, that constant you get, is your horizontal asymptote. So in our example, we saw that as I went towards infinity and negative infinity, why do I keep writing -3? That we got 1, right? So that means that y equals 1 is my horizontal asymptote. So the question is, do all graphs have horizontal asymptotes? Of course not. Polynomials definitely do not have asymptotes. Lots of functions, lines don't have, I guess a line is a polynomial as well, but there's lots of functions that don't have asymptotes. All right, so let's take a look at a couple of these functions. The first one is x squared. What does that look like? Well, we know that's a parabola with vertex 0, 0. And then we have 1 minus negative e to the x. So if I have a negative sign in front of e to the x, then that is a reflection across the x-axis. So I'm going to reflect across x-axis. And this 1 means that I shifted up 1. Now remember, if I was just graphing normal e to the x, I have an asymptote here at y equals 0. But this 1 shifts it up 1. So now I have this asymptote, y equals 1, and then it's flipped across the x-axis, so it looks like this. So if I'm just looking at this question, if I look at the x squared, are there any horizontal asymptotes of x squared? No, no asymptotes, vertical or horizontal. But on this one, there is one at y equals 1. And we should see that the limit as x goes to negative infinity of 1 minus e to the x equals negative infinity. All right, but how do we know how to find that if we didn't know what the graph is? So that's what we want to go into next. All right. I already said this, but polynomial functions, they do not have asymptotes. The limits as they go to positive and negative infinity are always positive and negative infinity. And if you remember, we had a chart of those. If the degree was even and it was positive, then both ends point upwards. If it was even and the leading coefficient was negative, they both pointed downwards. If the degree was odd, they pointed in different directions. All right, so we know polynomial functions. As we go to infinity and negative infinity, the y values also go to either plus or minus infinity. So how do we compute these other ones? All right, if I have a constant, so this is a constant, let's do an example like 3 over a polynomial with degree whatever, all right? It's saying x to the n. Let's do x squared. How can we figure out what that limit is? Well, anytime there's a constant over something that's getting really, really big, all right? So think about this fraction. If I have, let's just use x. That will make it a little bit easier. So I'm just going to make a chart. So if I have 10, I have 100, I have 1,000. Well, I get 3 over 10, 3 over 100, 3 over 10,000. Oh, I just have 1,000 here. I'll add one there. All right. So notice the denominator is getting bigger and bigger and bigger, but the top is staying constant, right? It's just a constant number 3. That means that fraction is getting smaller and smaller and smaller. And the bigger we get towards infinity, the closer that is going to get to 0. So anytime I have a constant number over something that's going to infinity or negative infinity, I am going to get 0. All right. So if I had negative 10 over x to the 5th, and I wanted the limit as x goes to infinity. All right, I have negative 10 over something that's just getting bigger and bigger and bigger. That means that number is getting smaller and smaller and smaller. So it goes to 0. All right, so now we're going to use that to compute limits of rational expressions. The way that we do this is we always divide by the highest degree in the denominator. All right, so I'm looking at this first question. And the degree in the denominator is x squared. Okay, so I'm going to divide every term by x squared. So I have the limit as x goes to infinity of 2x over x squared plus 3 over x squared over x squared over x squared minus 2x over x squared. Now let's reduce a little bit. 2x over x squared is 2 over x. I can't reduce 3 over x squared. I can reduce x squared over x squared. That gives me 1. And 2x over x squared gives me 2 over x. All right, and what we just said is if I have a constant over x to some power where that power is a positive real number, so my counting numbers, so I'm not thinking fractions, but my counting numbers, then they equal 0. That limit as it goes to infinity equals 0. So I know this equals 0, this equals 0, and this equals 0. So in the numerator, I get 0. In the denominator, I get 1, which equals 0. All right, that means I have a horizontal asymptote at y equals 0. And if you think back to when we talked about asymptotes before, we said if the degree of the numerator was smaller than the degree of the denominator, then y equals 0 is the horizontal asymptote. All right, why don't we try a few more? All right, this time the degree of the denominator is 2. So I'm going to divide everything again by x squared. All right, so I have a 2x squared over x squared. I have a negative 2x over x squared and a 3 over x squared. In the denominator, I have a 5x squared over x squared plus 6 over x squared. We're going to reduce. And in the top, I get a 2 minus a 2 over x plus a 3 over x squared. In the denominator, I get a 5 plus 6 over x squared. All right, now, remember anything with a constant over x to some power, that is a real number. positive real number, we are going to get 0. So this is 0, this is 0, and this is 0. So what I'm left with is 2 over 5. That means y equals 2/5 is my horizontal asymptote. Okay, let's take a look at the next two. One's going to negative infinity and one's going to positive infinity. All right, so let's start with the first one. We're going to do it just like we did the other ones. The degree of the denominator is 1, so I'm going to divide everything by just x. So I have 2x over x minus x squared over x over 2x divided by x plus 3 over x. All right, so go ahead and reduce. And I get a 2 minus x over 2 plus 3 over x. All right, so now if I plug in infinity, well, this is going to go to 0, like we said before. That goes to 2, that goes to 2, but what happens with this term right here? As x goes to infinity, it's going to negative infinity because there's a negative sign in front of it. If it was plus, it would be positive infinity. So I have an infinity in the numerator and the bottom is staying constant. So that means the whole thing is going off to infinity. In our case, negative infinity because of the negative sign right there. Now, what if I had the same problem, but I was going to negative infinity? All right, so if I reduce that, I'm not going to go through all the steps because it's the exact same thing as the last one. I have a 2 minus x over 2 plus 3 over x. Again, this one goes to 0, but now if I plug in negative infinity, I'm going to get a negative infinity, right? So I'm going to end up with a positive infinity. All right, the first one was negative infinity because there was a negative sign in front of the variable and we plugged in infinity, so it went to negative infinity. But now we're plugging in negative infinity and there's a negative sign in front. So we have a negative infinity, which gives us positive infinity. All right, so in that case, if it goes off to infinity, that means there are no horizontal asymptotes. Right? If it equals 0, there's a horizontal asymptote, or if it equals some constant, then there's a horizontal asymptote. But if you get plus or minus infinity, then there's no horizontal asymptote. All right. Let's take a look at our exponential functions. I know that y equals e to the x looks like this. And y equals e to the negative x looks like this. I like to rewrite this as 1 over e to the x. Okay, maybe I should draw it a different color. All right, so now let's look at the limit as x goes to infinity of e to the x. That's the purple one, right? So as x gets really big, what does the y value do? It just keeps going off to infinity. Now, on this example, we're going to infinity, but this time of e to the negative x, right? So what does that do? That goes off to 0, right? And there's a horizontal asymptote as at y equals 0. All right, now let's look at e to the x as I go to negative infinity. Well, that's this one here. It's going to that asymptote as well. So that limit equals 0. Now e to the negative x, that's here as it goes to negative infinity. It's shooting off to positive infinity. All right, so we're going to look for the horizontal asymptotes of this function right here. So the way that we look for them, we take the limit as it goes to infinity, the limit as it goes to negative infinity. So let's start by taking the limit as x goes to infinity of -3, 4 plus 1 over e to the x. Well, let's take a look at this 1 over e to the x. Now, it's not x to some power, but the numerator is staying constant and the bottom is getting bigger and bigger and bigger. So this goes to 0, right? And we know that from our graph up here as well. So what I get is -3 over 4. So there's a horizontal asymptote at y equals -3 over 4. Now let's take the limit as x goes to negative infinity of -3 over 4 plus 1 over e to the x. Now, as I go to negative infinity, what does this denominator go to, right? The top is going to stay constant, right? This is 4, but this part right here is going to go off to infinity, right? So I get a -3 over something that's getting bigger and bigger. What does that mean? That means that limit is 0. So we have two horizontal asymptotes. One as it goes to positive infinity is -3/4, and one as it goes to negative infinity, which is 0. All right. And that is the end of lecture 11. We will pick up on Monday, lecture 12. We'll continue on limits, left-sided and right-sided limits. So have a good weekend.